Have you ever just stopped and wondered, what do you, the air you're breathing right now, and the most distant star in the galaxy all have in common? Well, today, we're going to be detectives. Our mission? To understand the fundamental stuff that makes up our entire universe. And it all starts with a question.
Yeah, it sounds like a riddle, right? A star, a stone, a drop of water? But the answer is actually super simple. They're all made of matter. That's just the scientific name for stuff. Everything. The phone in your hand, the chair you're sitting on, even the air itself. It's all matter. The easy definition is just anything that takes up space and has mass. But that just opens up an even bigger question.
What is matter, really? I mean, on the deepest, most fundamental level. For centuries, this question sparked a massive debate. Was the world one continuous block, like a piece of wood that you could just keep cutting into smaller and smaller pieces forever? Or was it more like a beach, made of countless tiny individual grains of sand? To figure that out, we need to look for some clues.
To solve this mystery, we've got to look at the evidence. And our very first clue comes from a surprisingly simple experiment you could totally do in your kitchen right now.
Okay, picture this. You fill a glass with water and mark the water level with a pen. Then you take a spoonful of salt and stir it in until every last crystal disappears. So what do you think happens to the water level? It should go up, right? I mean, we just added a bunch of salt to it. But here's the twist. It doesn't. The water level stays exactly where it was. So now we've got a real puzzle on our hands. The salt is definitely in the water, but it's not taking up any new space. How is that even possible?
And this one observation cracks the whole case wide open. The only possible explanation is that the tiny little salt particles are slipping into empty spaces that are already there between the water particles. It's like pouring sand into a jar full of marbles. The sand just fills in the gaps. And there's our proof. Matter isn't one solid block. It's made of individual particles. That old debate, the particle theory wins.
So just how tiny are we talking? Well, get this. Just 2 or 3 little crystals of a chemical called potassium permanganate can turn 1,000 liters of water bright purple. The only way that's possible is if each of those tiny crystals contains millions of even tinier particles that spread out through all that water. These particles are almost unimaginably small.
All right, so knowing that particles exist is just step one. The next part, the really cool part, is understanding how they behave. And it turns out all of these countless trillions of particles follow a very simple set of rules. 3 secret laws that explain pretty much everything about the physical world. And here they are. First, space. Just like we saw with the salt and water, particles are not packed together perfectly. Second, motion. They are never, ever still. They're constantly vibrating and bouncing around. And third, attraction. They have a force that pulls them toward each other, kind of like tiny little magnets. Space, motion, and attraction. You got to remember those 3 because they explain everything that comes next. Let's zoom in on that motion rule. The energy of a moving particle has a name. It's called kinetic energy. And here's the key. When you heat something up, you're not just making it hot. You're literally giving its particles more kinetic energy, which makes them move faster and crazier. This is exactly why you can smell hot food from all the way across the room. Those little aroma particles are moving so fast they can travel through the air right to your nose. And all this constant moving around leads to something called diffusion. It's really just the natural mixing of different kinds of particles. Think about putting a single drop of ink into a glass of water. You don't have to stir it, do you? The ink and water particles, just by doing their constant random dance, will mix all by themselves until the color is spread out evenly. That's diffusion, right there, in action. So this brings us to a really big question. If everything is made of particles that follow the same 3 rules, why is a rock hard, water wet, and air invisible? Well, it all comes down to a constant battle between 2 of our rules, that kinetic energy pushing particles apart and the force of attraction pulling them together. The winner of that battle determines if something is a solid, a liquid, or a gas. This table basically lays out who's winning that battle. Just look at how you go from solid to gas. The particle attraction goes from very strong all the way down to very weak. And that one single change is the reason for all the other differences we see. Let's take a closer look at each one. So in a solid, the forces of attraction are winning, big time. The particles are locked into a fixed position, packed in super tight with very little space between them. They can't really go anywhere. They can just vibrate in place. And that's exactly why solids have a definite shape and volume. They are rigid. Now, in a liquid, it's more of a tie. The attraction is still strong enough to keep the particles really close together, and that's why liquids have a definite volume.
but their kinetic energy is high enough that they can break free from their neighbors and slide past one another. This is what allows them to flow and take the shape of whatever container you pour them into.
And then we have a gas. Here, kinetic energy wins by a landslide. The attraction forces are totally overpowered. The particles are moving so incredibly fast and are so far apart that they barely even notice each other. They just fly around randomly, bouncing off everything. And that's why a gas will always expand to fill whatever space you give it.
So you see, a solid, a liquid, and a gas aren't really different kinds of things. They're just the same particles at different energy levels. And that means we can actually force them to change state just by tipping the balance in that battle between motion and attraction, usually by using heat.
So let's follow the journey of water. You start with solid ice. As you add heat, its temperature goes up and up until it hits 0 degrees Celsius. But then, something really weird happens. As the ice is melting into liquid water, the temperature gets stuck at 0. Once all the ice is melted, the temperature starts to rise again until it hits 100 degrees Celsius, the boiling point. And, you guessed it, the temperature gets stuck again at 100 while it turns into steam.
This is a fascinating puzzle, isn't it? You are continuously adding heat to that melting ice, but the thermometer's reading just isn't changing. So where is all that energy going? It feels like it's just disappearing.
The answer is a concept called latent heat. Latent literally means hidden. During a change of state, all the heat energy you add is hidden from the thermometer. Instead of making the particles move faster, that energy is being used for one specific job, breaking the forces of attraction that hold the particles together. It's the energy you have to pay to go from an organized solid to a flowing liquid.
Now, most things go from solid to liquid to gas, but some substances like to take a shortcut. Sublimation is when a solid turns directly into a gas, skipping the liquid phase completely. A perfect example is dry ice, which is just solid carbon dioxide. It never melts into a puddle, it just turns directly into a gas. And the reverse of that, going from a gas straight to a solid, is called deposition.
Okay, so understanding all this isn't just for a science lab. These principles explain things that happen all around you every single day, especially one we really rely on, how things cool down.
It all comes down to evaporation. For a liquid particle to escape and become a gas, it needs an extra boost of energy. So where does it get it? It steals that energy from its surroundings. This theft of heat is what we feel as a cooling sensation. It's the entire reason sweating works to cool you down. And you can speed this process up with more surface area, higher temperatures, and more wind, which, by the way, is the perfect recipe for drying your clothes on a clothesline.
So let's end with a final test. You know the secret rules of matter now. You understand kinetic energy, you get how states change, you know all about evaporation. So you can definitely answer this. Why does pouring hot tea into a saucer cool it down so much faster than leaving it in the cup? The answer lies in the very principles we've just uncovered. You see? The science isn't in some far-off lab, it's right there in your kitchen.